Welcome back to the Vedic Astrology podcast. My name is Fiona Marks. Coming up,
Totality for an astronomer is all. Totality is all. And totality is when the moon will completely block the sun. Clearly, the sun's important to us because without it, we've got no photosynthesis and we're all dead. So understanding the sun is a really key thing for astrophysicists. The sun is throwing off high energy particles all the time and they're streaming towards the Earth, and it's called the solar wind. The solar wind can have quite a devastating effect on satellites in orbit, and we are utterly dependent upon the satellites which are up. Now, electromagnetic waves transfer information without the need of a physical medium. You don't need a material involved, so they can travel through a vacuum. So they are made up of self-sustaining electric and magnetic fields. We invented dark matter. We still don't know what that is. It's so amazing. We still don't know what it is. Modern cosmological theory, the standard model of cosmology, still assumes that dark matter exists. Then dark energy was produced. We still don't know what it is. But all the modern theories of cosmology and astronomy basically assume it's out there. The fabric of space itself basically starts to shake. And so the waves can pass through space itself. It's just not light or anything. It's space itself moving.
Hello, everyone. Welcome back to the Vedic Astrology podcast. My name is Fiona Marks. I'm quite excited today because we have a big astrological and astronomical event coming up next week, which is the solar eclipse on the 12th of August. And I have invited my friend and astronomy educator, Stephen Jones, back to the podcast. Hi, Stephen. It's great to see you again.
Good afternoon, Fiona. Lovely to see you as always.
This eclipse that we're having is pretty special. I guess astrologers we always love eclipses. It's a bit of excitement in our year. But this one's particularly special for those of us living here in Portugal because it's going to be visible for us. And I don't know whether you know this. This is Saros Series 126 eclipse. And this is the very eclipse. The first one of these was in 1179. The same year that Portugal was recognised as a kingdom on its own right. So for Portuguese people, this is a launching eclipse, a beginning of our country. And it just happens randomly that it's going to be visible for us. But is there anything in particular that makes this eclipse astronomically significant?
Unfortunately, in terms of eclipses, it's almost mundane. It's not particularly the shortest, it's not particularly the longest. What the key thing is, and this is where we get this sort of switch out, don't we, between the astrophysics of it and the personal. The key thing is, personally for me, is that I'm going to get to see it. I'm going to wind things back a little bit, and we're going to go back to 1999. Now, okay, 1999 was the last time that I saw, now we're going to get our terminology right here, a total solar eclipse. So you have to send yourselves back. So you guys who maybe are a little bit older enough, we're back in the 90s, rave culture, all those sorts of things. And in the UK, down in Cornwall, which is down in the far southwest peninsula of England, you were able to see a total solar eclipse. So an eclipse is, in astrophysics term, we would talk about occultations. So an occultation in astrophysics is when one astronomical body moves in front of another. Now, occultations are taking place all the time. And so many of the occultations that we would think about are from an Earth-centered view. But of course, you get occultations throughout the entire solar system and throughout the universe, depending upon your points of view. And so one of the special occultations for us on Earth are the solar and lunar eclipses, which I guess we need to talk about as well. So if we think about the moon orbiting the Earth, the moon is always casting a shadow. The moon is always casting a shadow. And the shadow cast from the moon is generally just into space. And there isn't really any sort of relevance of it to the Earth. The Earth, of course, is casting a shadow behind itself as well. And so we experience that in terms of nighttime. So as the Earth spins in its orbit and then we enter into the dark bit. But if we're up in an aircraft, then we're effectively flying in behind the Earth's shadow. So the Earth and the moon both cast shadows from the sun. We often think about orbits just being circular. And some of the greats, like Ptolemy and Copernicus and Galileo, thought that orbits were circular. Johannes Kepler's work in the 17th century, he realized that orbits are actually elliptical. So they're not circular, they're more like an oval shape. So the moon orbits the Earth in an ellipse, in an oval. But also, if you look at the plane of the orbit, it doesn't orbit at the same angle which the Earth orbits the sun. So the plane on which the Earth orbits the sun is called the ecliptic. And the moon orbits the Earth, but not on the same plane. It's off by about 5 degrees, I think it is. And so as the moon orbits around the Earth every about 27.3 days, you don't get an eclipse every lunar orbit, because to get a total eclipse of the sun, then the moon basically has to block out the sun. In other words, the shadow cast by the moon is going to have to end up on the Earth's surface somewhere. So because the orbits are at a slightly different angle, it means you don't get a total eclipse every year. You don't necessarily get a lunar eclipse every year. And you've got to wait for the positions for everything to line up. So that's what's going to be happening next week. So the positions are lining up in such a way that we think about the shadow cast from the sun and the sun's rays hitting the moon, and then the shadow behind the moon. The shadow behind the moon actually decreases inside in the cone, and you get these things called the umbra and penumbra. And the key bit is the sort of the central cone where you're going to get complete shadow. And it just turns out that shadow, it almost reaches zero size by the time it lands on the surface of the Earth. There's been a lot of misinformation I've noticed online, people talking about the eclipse, and it's almost like it's the same everywhere, and it really isn't. In Portugal, most of Portugal, you will see a very impressive partial eclipse. And the moon will start to move across the face of the sun sometime in the afternoon. It will depend upon your exact position when that will start to happen, but it'll be later on in the afternoon, probably about 4 o'clock or so. And the moon will start to pass over the surface of the sun. And certainly in large parts of Portugal, you're going to see 90% of the sun covered. You might even notice a slight dimming of the light. You may even feel it gets slightly cooler. And so you will actually notice this. But totality for an astronomer is all. Totality is all. And totality is when the moon will completely block the sun. Now, so let's head back to 1999. The path of totality crossed Cornwall. Now, it started off somewhere up in the North Atlantic. And the path of totality, and we say it's a path because it doesn't just stay in one place. Because, of course, we've got a very dynamic system of the moon orbiting the Earth and the Earth orbiting the sun. The actual point to where the shadow is landing on the surface of the Earth is moving. It's moving very fast. And so the path of totality was going to cross over Cornwall. And if you're in a fixed position, some people go chasing them in planes. And so to try to keep up, and even in jet planes, NASA sends jets up to look at the eclipses. The jets can't keep up with the rate at which the shadow is moving. So that gives you a sense how fast it is. So I sat there with my mother and had her little Cocker Spaniel Smokey. And we sat there on the coast at Cornwall in a beautiful spot. And during the morning, the clouds came in, and it got cloudier and cloudier and cloudier until it was totally covered. The sky was completely covered. It was the only place in the whole of the UK which was cloudy. The rest of the UK was clear. And it was in August. And the problem was, there was no point in me saying, okay, I'm going to go somewhere else, because it wouldn't be totality. And the path went over Cornwall, then across the English Channel and into northern France. And of course, you've got a lot of sea. You can't just move. And so we sat there, and I had a look on the time, and then it got to the moment, and it was very odd, and it just went very dark all of a sudden. And the streetlights came on, the birds stopped singing, and everybody clapped and cheered. And it was very weird. And we waited about 2 minutes, 2.5 minutes. And then all of a sudden, it just came light. And it was almost that second bit was the weirdest, as you were like sitting in a room, you switch the light switch on, but you're sitting outside. That doesn't happen when you're outside. And it all just goes woof, and the lights came back on. So I have experienced a total eclipse, but not really. So we bring ourselves to next week. We've known about this eclipse for a very long time. We've got systems that basically can predict where the eclipses are going to happen thousands of years into the future. So I know all about this. I've been planning this for years, oh my. The path of totality, it's really weird, this one. It actually starts in northern Russia, heads across the Arctic, drops down, actually it's passing right over Reykjavik. So that could be quite fun. But Reykjavik's a bit dodgy for weather. Cross the North Sea, and then the path of totality will cross northern Spain, and then it's going northwest to southeast, right across Spain, the path of totality. Right the way across Spain, and then out the other side, and then I think it even ends in the Balearics somewhere. It's quite a late one, so totality, in terms of Spanish time, it's going to be about 8:30-ish in the evening, only about an hour before sunset, so the sun's going to be quite low in the sky. And so in terms of, again, of an eclipse, it's pretty standard. It's not particularly long. The eclipse being quite late in the day is a little unusual. So I'm afraid, in terms of the normality of an eclipse or not, it's a pretty standard one.
That's good. That's what we like. We don't want any anomalies. And then during eclipses, scientists like to do experiments and observations. Are you aware of anything in particular with this eclipse?
The corona is the outer atmosphere of the sun. We've got all these different layers of the sun. We've got convective zones and things inside the sun, and we've got the core where nuclear fusion is taking place. And then we've got the photosphere, which is just the surface. The corona is the outer atmosphere, and it's impossible to see in normal conditions. Now, the corona is actually quite a diffuse gas. It's mostly hydrogen and helium. It's at about 1 million degrees. And so it's very, very hot. It's not as hot as the core of the sun, but it's significantly hotter than the surface. Surface of the sun is only about 6,000. I'd say only. That's not that. In the labs at school, we got Bunsen burners. We can get them all up to 1,000. But the corona is 1 million degrees. And the corona is very interesting because we think that the corona can actually learn more about the surface of the sun and what's going on beneath it by studying the corona. Now, we actually have spacecraft which are placed at some of these things called the Lagrange points, which are a gravitational equilibrium, where you can put a spacecraft which sits all the time directly between the sun and the Earth. And so we have spacecraft sitting at these Lagrange points looking at the sun. And they actually have like little physical discs built into the camera systems that block the sun out. But the discs have to be significantly bigger than the sun for the system to work. The beauty of watching an eclipse on the surface of the Earth is that you only just cover out the sun. And so we actually get to see the corona right down close to the surface of the sun. And it gives us much more information about what the photosphere, the surface of the sun, is doing. Now, clearly the sun's important to us because without it, we've got no photosynthesis and we're all dead. So understanding the sun is a really key thing for astrophysicists. But also solar weather has become so much a bigger issue over the last 100 years or so. Because the sun is throwing off high energy particles all the time and they stream towards the Earth, and it's called the solar wind. The solar wind can actually impact electrical systems, particularly near the North Pole and the South Pole. But also the solar wind can have quite a devastating effect on satellites in orbit. And we are utterly dependent upon the satellites which are up. Not sure if people fully appreciate how dependent we are. And it might be, oh, we can do like GPS on our phone or whatever, or you get pretty pictures. It's so much more than that. And so we are utterly dependent upon our satellite systems. And so understanding solar weather and the sun is a really big deal scientifically, but also in a very practical sense of how we actually run electronic systems and satellites on Earth. And so seeing an eclipse from the Earth and being able to see the corona all the way down is very important. And that's why lots of instruments will be trained at the sun. NASA will have planes up there flying, chasing it, looking at the corona. Could I just say something about safety at this point?
Yes, that's a great idea. Let's do that.
Any viewing you do of the sun, always you have to be careful. Now, the thing is, it's not if you just quickly glance at the sun, you're going to go blind. You're not. But it's surprising how little amount of time directly looking at the sun, a few seconds of actually peering at the sun, can be really problematic, can actually start causing eye trouble. And so you shouldn't try to watch the eclipse just by quickly looking up at it. You've basically got a couple of ways of doing it. The totally safest way is to just follow it online, but it's not quite the same, I get it. But that is the absolute safest way. The next sort of, if you're going to actually try to observe it, you really need to have some eclipse glasses. And they're generally made of cardboard, most of them, and they will have filters in the front of them. They're not just dark pieces of plastic. They will look almost like a sheet of tin foil, and they will cut out 99.91% of the electromagnetic radiation coming. Those are the best thing to view the partial eclipse, which most people is that will be seeing. I'm afraid if you haven't got eclipse glasses by this point, if you go on Amazon and you've got Amazon Prime and you can do a 24-hour delivery or whatever, you might still be able to get all the sun, all right? You're generally not buying them in shops very easily. So if you haven't got eclipse glasses by now, that could be a bit tricky. But you could actually attempt to make something like a simple pinhole camera. And obviously, if you just go onto YouTube and go make a simple pinhole camera, you will be able to actually observe it. Now, I've got some eclipse glasses. Being there and experiencing it and seeing the corona, seeing the prominences, the eruptions that blast off the surface of the sun as big as the planet Earth itself. Hopefully we're going to see some of these because the sun's quite active at the moment. We're just going to experience it. So I'll be watching it with eclipse glasses up until, and as soon as we get the diamond ring is the first thing that happens, as it's almost covered it, and the last sort of part of the sun is still visible. That's called the diamond ring. And really, you should still really have eclipse glasses on for that point. It's depending at what point I'm going to flip them off and see. You also then get this thing called Bailey's beads, named after this astronomer called Bailey. And Bailey's beads is where you actually get the sun's rays passing through the valleys between the mountains on the surface of the moon. And so instead of having this one bright diamond, which is part of the ring, you might get these little bits. And then the moon will move completely across it. And at that point, the sun is blocked out, it will go dark, the corona will appear, and I'll try not to cry too much.
Yeah, we're wishing you a wonderful experience of this eclipse. When I was looking into the research for today, I don't know whether you know anything more that you can add to this, but apparently a team in Spain, LUNEX, is going to be repeating Eddington gravity lens experiment. People might be aware of that. I'm only aware of that because there's a movie called Einstein in Eddington and it has David Tennant in it. So people might have seen it and that's seen it. Can you explain a little bit about why this is significant, what this experiment really proved?
I suppose it comes, a little bit of it is where I was talking earlier about orbits being circular. And Ptolemy, back in the whatever century BCE, obviously had this view of these circular orbits, and Copernicus and Galileo often thought that orbits were circular. And so and then Copernicus, we realized that orbits were elliptical. Okay. One of the things is that we felt like we had a very good handle on the orbits of the planets. But when they started looking at the orbit of Mercury, they noticed that it wasn't following the path exactly described by Newton's laws of gravity. But by this point, once we got these really good observations, Einstein had already produced his law of gravity. So when we're thinking about the action of gravity and what it is, for most occasions, Newton works brilliantly and he is very successful, but it doesn't work in all situations. And in some of the more extreme situations where you've got stronger gravity fields, we actually have to introduce Einstein's view of gravity and how he views space and time and how large mass objects can warp and distort space-time. And so that can actually change the orbits. And so when we applied Einstein to the orbit of Mercury, for example, it all worked out again and everything was great. But in an attempt to try to verify with more detail some of Einstein's views, they particularly wanted to take observations of stars during the total eclipse. Now, we generally can't see stars during the daytime, and that's because the brightness of a star is so significantly less than the sun. We can't see the stars. But during a total eclipse, it gets so dark that stars should appear, and I should be able to see stars up there near the sun. Now, what they did is that they know exactly when the eclipse is going to happen. They know exactly the position of the Earth and the moon in the sky. They know exactly which stars are going to be close by. And what Eddington did, he was trying to look at stars which were really close to the sun at the point the eclipse happened. Now, we know exactly where the stars are. From Ptolemy, again, gave us some great star charts. The great Islamic astronomers in the sort of the Middle Ages, they produced some wonderful star charts. We know exactly where the positions of all the stars were. But what Eddington realized using Einstein's general theory, that the sun is so massive, it actually distorts space around itself, such that a ray of light coming from this distant star, as it goes past the sun, it effectively sort of bends around it. And so instead of the starlight hitting us directly in a straight line, it actually makes a little bend. And that means the position of the star should shift slightly. And that's what they were looking for. So they predicted what the shift in the positions of these stars should be near the sun. They took measurements of the eclipse using cameras and photographed it. And indeed, this is perfect bit of science. We got some theory. The theory makes predictions. You then go out and test the predictions, and guess what? The stars moved exactly by the predicted amount that Einstein gave us. And so monitoring eclipses, we're able to verify Einstein's general theory. Now, we don't really need to verify Einstein's general theory because it is so well known. We might come back to that in a second. But again, I did read about this. Yeah, so there's a team actually attempted to repeat it, which is lovely. Not an easy thing to do because the photograph, you got to get photographs taken before the eclipse and then during the eclipse. And yeah, difficult thing to do. So that's really lovely.
Yeah, nice. And then I didn't think about this, but when it does go dark, when you're there in Spain, will you be able to see Jupiter, for example, traveling near the sun at the moment from our perspective? And Mercury, but I think Jupiter is closer. So I'm just wondering, do you think you might see Jupiter in that?
That's a good question. And no, it's a really good one. I've never seen Mercury with the naked eye. I've only ever managed to see Mercury with a telescope.
Okay.
Because Mercury is so close. No, it looks like at the moment of the eclipse, Jupiter is right on the horizon.
Yeah, okay.
And
Mercury will have already be below.
They're going to be really close to the horizon. It's possible that I might be able to. I think Jupiter and Mercury are going to be way too close to the horizon to actually see.
Yeah.
And that could be quite tricky. But Mercury, see, a lot of it will depend upon, again, I've picked somewhere which is pretty flat. So I haven't got anything close to me. So I might get lucky. That's
all right. I'll be putting in the call next week and see. You can tell us whether you saw it or not.
That's great. That's a really great question, though. That's a really great question.
I mean,
I've seen Jupiter lots, but to see Mercury,
yeah.
That would be amazing.
All right, have to get yourself up on some kind of cherry picker or something.
Yeah, all right. Absolutely. So I think we've maybe covered eclipses. Actually, can I just throw in one other thing here?
Yes. Yeah.
There is another type of eclipse that people may or may not have heard of called an annular eclipse.
Okay.
Not annual, but annular. So annular, which is related to circles.
Yeah. And like in Portuguese, our anel, right? Your rings are.
Now, because if you get to this special moment where the Earth, the moon, and the sun are all lined up and everything's in a line, you think, fantastic, totality, we're brilliant. But remember, the moon orbits in the ellipse, which means sometimes the moon is slightly further away from the Earth, sometimes it's slightly closer. And when you have an annular eclipse, it just turns out that when everything lines up, it's during the point where the moon is slightly further away. Now, if the moon is slightly further away from the Earth, that will mean the moon will look slightly smaller in the sky, which means it doesn't block the sun out, and you just get this ring of fire, and you just get this bright ring, and the moon will sit in the middle of it. So you couldn't, with the naked eye, for example, it'd be too bright. And it's not totality, the corona doesn't appear. If it had been an annular eclipse, I would have been devastated, but it's not. It's the classic total eclipse. And we've actually got another total eclipse coming up next year. And totality is actually going to be able to be observed right from the south of Spain. But you're going to have to be right down in the south. You'll have no control much about where you're going to go. If it looks like the weather's looking dodgy, you're stuffed. You're not going to be able to see totality. But we will be going.
All right, we'll get back together and see if there are going to be any planets involved at that time. But now we've been talking about all of this, I want to bring in a little bit of astrology as well. So I practice Vedic astrology, and one of the words in Sanskrit for Vedic astrology would be Jyotish, the study of light. And I think that's why eclipses are kind of so fascinating for humans, for astrologers, because of what you were describing. From even a fully clouded over day, you had this bizarre sense of the loss of light and then the regaining of light. Even our own bodies, their senses are going off and saying something is just not right. So I was wondering if you could share with us a helpful way for us to understand light as part of the electromagnetic spectrum. How can we get our heads around what we consider to be light is part of a whole experience of what photons do?
So we've got a few things. If we think about the EM spectrum, electromagnetic spectrum, it's a family. Often the word I use to my students is like a family of waves. And within all families, there are things which are similar in some families, and there are some things which are very different. Now, a wave, if you want to get down to the basics of it, a wave is a means of transferring energy or information from one place to another. Now, you can have mechanical waves which require a physical medium. So like water waves, for example. Generally, water waves are produced by the wind blowing over the surface of the water. You can have other things make them, like tsunamis and such, but generally, most water waves are produced by the waves blowing over the surface of the water, which causes the water then to start to distort. And so this distortion, the energy of the wave, the up and down motion will travel across the surface of the water, and that's mechanical wave. Sound is a mechanical wave as well. If you don't have water, you don't have air, you can't have the waves. But there are means of transferring energy from one place to another. Now, electromagnetic waves transfer this energy or the information without the need of a physical medium. You don't need a material involved, so they can travel through a vacuum. So they are made up of self-sustaining electric and magnetic fields. There's some fancy maths in this, which was all worked out by this guy called Maxwell in the late 19th century, one of the great geniuses of science. And so Maxwell understood the electromagnetic waves as these electrical magnetic fields that interact with each other and they can travel through space. So at one end of the spectrum, we have radio waves, and the radio waves, they have a very long wavelength. So if you think about often, if you head down to the beach at Ginshu or something, you can see the waves coming in. And if you head up to the hills above, you can actually look down and you can see the distance between the waves. And that distance is called the wavelength. You can't see radio waves, but they have a wavelength, and the wavelength can be kilometers long. So they can be ridiculously long, and they can also just be a few meters.
For those of us who are old enough, Stephen and I think similar age, pulling the antenna on our radio back in the day, the longer we made the antenna, that was partly to maybe catch this wavelength?
That can control it, yes. So the physical size of the aerial you use did affect what sort of wavelength of radio waves you could detect. And so the size of the detector is related to the size of the waves.
Okay.
And so that generally why radio telescopes, for example, tend to be huge. The Arecibo Radio Observatory, for example, had to be massive. It was such a shame that cables snapped and it collapsed. But you generally have to build them very big because the wavelengths are generally quite long.
And these are like big dish things?
Yeah. So you used to have a dish. Satellite TV is not a massive thing in Portugal, but you will see people with dishes on the sides of their houses. And what these dishes can do is that they can collect the radio waves from a satellite, and the waves will hit the dish, and then the dish has got a specific shape, so the waves can then reflect off the dish to a receiver, and so you can then pick up the signals from a satellite. And astronomers also use radio telescopes to actually pick up radio waves from deep space. Certain objects produce radio waves, and we can use these things to study them. So you can then go through the whole family of the waves. So radio waves is the longest wavelength, the lowest energy, generally the least dangerous. Then you get the next one is microwaves, which is a few centimeters long. Again, pretty low energy, not really dangerous. I know if you climbed inside your microwave oven, you probably wouldn't have a good time. And of course, your phones produce microwaves. Now, of course, some people say that these things are dangerous. I would personally say that these are not dangerous because of the microwaves. They may be dangerous for other reasons, texting while you're driving, for example. But the energy producing microwaves is still very low. Then after the microwaves, you've got infrared. Can we detect radio waves? Not really. As a person, I can use technology, but can I physically? No. Could I physically detect or experience microwaves? Yeah, I guess. Put my hand in a microwave oven, it would get hot. Infrared, we can detect it. It's what we feel as heat. Your grill or your toaster will actually cook things via infrared. So the wavelength is getting shorter and shorter. Now with microwaves, it was a few centimeters. Infrared, we're now down to a fraction of a millimeter. The next one along is light. Good old visible light that we think about. And the wavelength of visible light is about 1,000th of a millimeter. The thing is, though, is that we can't actually detect very many wavelengths of visible light. And the thing is, we call it visible light only because those are the ones we can see. Now, over millions of years, our eyes have evolved in such a way that they can detect this very specific part of the EM spectrum. And so we call that visible light. I show my students these graphs showing the energy output of the sun. And the sun emits all 7 parts of the EM spectrum, but it doesn't emit them constantly. And you can actually plot a graph of this. You can point a detector at the sun, you can plot it, and it goes up to a peak and then drops back down again. And you look at the peak of it, and the wavelengths at which the sun produces the most energy is visible light. As I said to the kids, it's amazing. It's an incredible coincidence. So I was like, oh yeah, it's not a coincidence. Life on Earth has evolved to detect.
Because of exactly this, yeah.
Hotter stars, for example, produce, if you had a particularly hot star, surface temperature of 20, 30, 40,000 degrees, then the peak may actually move out of our visible into the next one along, which is ultraviolet. And so you might have life on the planet around one of these really hot stars that sees in ultraviolet. And they may even experience colors of ultraviolet. Our eyes have evolved to detect different wavelengths of light. So we perceive that as color variation, which helped us to pick fruits.
Poisonous.
Absolutely. But you notice how it's getting radio waves, not that dangerous. Microwave, not really. Infrared, you could burn your hand. Visible light, if you get enough of it, you could blind you. Ultraviolet's getting more dangerous now. So too much UV can be a problem. Being a fair-haired person living in Portugal, I have to put block on or whatever if I go out in the sun. But the wavelengths are now getting shorter and shorter. And after ultraviolet, we then head into X-rays. We're now 10 billionth the width of a meter for the wavelength. And then even shorter, the last one is gamma rays. And so the visible part is just a tiny little part of the electromagnetic spectrum. So we perceive so many parts of it. So our bodies can detect pretty much all of them apart from radio waves. Our bodies can detect X-rays and gamma rays because if you get too much X-rays and gamma rays, your body will react in ways which are not that good. A little is fine, and a little it can be very helpful if you're using X-rays to look at the body. Ultraviolet, again, gives you a tan. As long as your skin doesn't go red, then it's pretty much fine.
Is it used also for sterilizing, ultraviolet? Is that when they sanitize things?
Yeah. You can use it like that. The ultraviolet can kill cells. It can kill our skin cells, but it can also kill cells that are not particularly that good. And some people have ultraviolet sterilization lamps, for example, in their fish tanks, and they can pump the water through like a UV light, and it can do that. But of course, not all animals use visible light. So there's lots of insects will use visible, but also will see into the UV. And so there are lots of insects that can see partly in ultraviolet. There are a number of animals, certain types of birds, for example, that can see into infrared. You generally find that plants that have red flowers tend to get pollinated by birds because the insects don't see the red. And so they might give off some scent, for example, so they might be able to smell it, but they won't see it. Plants that tend to have bluish type flowers are generally more likely to be pollinated by insects. And then, of course, other creatures will use other types of waves. And so bats and dolphins, for example, can use sound, for example. And so sound can carry information, and so they can perceive the world around them. And of course, if anybody went to see Project Hail Mary or read the book, I would recommend both, to be honest. I love the book and I love the film. We've got a form of alien life that perceives the world around them by using sound. Because the way that Andy Weir wrote the book is that they live on a planet that is deep in a very thick atmosphere. So no light gets to the surface. So they perceive the world using sound. So all of Rocky's technology is very tactile, and it has lots of different shapes on it. When he eventually goes on board his spaceship, there's no color anywhere because that's meaningless. There's some of the things about light.
Yeah, I know. It's hard to get a head around. Let me just wrap up there. When you're talking about sound, like sonar, that's not on the electromagnetic frequency,
Correct.
is it? It's on the mechanical wave that you're talking about.
It's a mechanical wave, not an electromagnetic wave. So I was talking about this weird family. All parts of the EM spectrum can go for a vacuum. They're all things called transverse waves. They all go at the same speed in a vacuum, which is the speed of light, 300 millimeters per second. So they have many similar things about them, but then they also have lots and lots of things about them which are very different. So again, different means of production. Some have different uses. Some are highly dangerous to organic matter. Some are not dangerous to organic matter at all. Sound is a mechanical wave. Speed is generally significantly slower. So the speed of sound in air is only about 330, 340 meters per second. So that's how we can really perceive the difference between like a flash of lightning. We can see the flash and then can wait a few seconds before we hear the thunder. And it's because the light is a million times faster than the sound. The sound, not EM spectrum whatsoever.
And sound doesn't work in a vacuum.
Correct.
Because it's got nothing to bounce off.
I often, with my students, I'll get them all stood in one straight line with their hands resting on the shoulders of the person in front of them. And I'll go at the back, push them forwards and backwards. And then they start moving forwards and backwards. And because they've got their hands on the person in front of them, they start moving forwards and backwards. And the vibration passes through. But it is a wave. And it has many of the properties of a wave.
All right. We're talking about Jyotish being the study of light. And we're realizing that this study of light is actually a whole spectrum, which in some ways we can get our minds around thanks to your explanation. When we're seeing these light from the stars, so we just talked about the eclipse and the sun being dimmed by the moon coming in front of it from our perspective. Tell us a little bit about the light that we're seeing with our eyes, that maybe you'll see Jupiter or you'll certainly see some other background stars. That light is part of this frequency that we can see. It's been traveling through space for thousands and thousands of kilometers.
Yeah, or significantly greater than that. The moon is 350,000 kilometers away, something like that. It takes about a second for a ray of light to travel from the surface of the moon to Earth. And of course, the only reason we see the moon is that it's not a luminous object, it's a reflective object. So the moon doesn't produce any visible light of its own. It will produce some electromagnetic waves. So for example, the moon will produce infrared. So you could point an infrared telescope at the moon and you could observe it. even if it completely blacked out, you would still observe some of the infrared. But in terms of visible light, light bounces off the surface of the moon. Some of it will reflect towards the Earth, and we see it takes about a second. So when you look at the moon, you're actually seeing it as it was about 1 second ago. You're seeing it in the past. Our whole sense of what is now and what is future and past really gets affected by this. I think Neptune is about 4 light hours away. It takes about 4 hours for the ray of light from Neptune to reach the Earth. The closest star to us other than the sun is Proxima Centauri, and that's about 4.25, 4.26 light years away, because kilometers become meaningless at this point. So it takes more than 4 years for a ray of light from Proxima to reach us here.
Yeah.
So the ray of light is traveling through space, which is pretty much a vacuum, not perfect vacuum, but pretty much. And we can see objects further and further out. And with our naked eye, generally we're only seeing things a few hundreds or a few thousand light years away. So it's all relatively close stuff. Because the further away you are, by the time the light gets to us, it'll be so dim because the light rays spread out as they travel. So the intensity gets less and less. And so really distant objects, we generally don't see with the naked eye. And that's why we need telescopes.
And in terms of the planets that we look at, do they have light of their own, or we're just seeing the sun's light bouncing off them?
Sunlight's reflected. And so when we see the planet, what you're really seeing is light reflected from the sun. So the sunlight is head on out, potentially quite a long way, hit the object, reflected, and come all the way back.
Yeah. Great. And you were saying when we were talking about the electromagnetic spectrum that you can encode information in these waves, or these waves can carry information?
Yeah. I suppose you can think of that in a number of different ways. Smoke signals is a way of carrying information via light, because you can set off smoke and you can see the smoke. So the way that you're receiving information is by visible light. And so different patterns of smoke can mean different things. We had semaphore, which was like sets of flags. And if you're seeing a flag, then you're observing, experiencing it via visible light. And then, of course, you have things like Morse code. And in the Second World War, you would get situations where ships would be sailing next to each other. And they could use radio to speak to each other, but actually radio signals will travel out and somebody else could detect them and you could attempt to encrypt them or something. But actually, if you're just sailing right next to somebody, you could have a big lamp and you could switch the lamp on and off. And so by using a set of flashing lights, you can carry information that way. Now, in a way, we've gone on with that. And so modern computer systems, for example, we can convert information into a series of ons and offs, ones and zeros, which is connected with the concept of digital and binary. So fiber optic cables, we have lasers attached to the ends of the cables. The lasers turn on and off very rapidly, millions of times a second. And these flashes will travel along the optical fibers to the receiving point. And so we can send information. The modern internet as we experience it wouldn't be able to exist without the fiber optic cables. And interestingly, we utilize the telecommunication satellites less and less. Most of the data which travels around the planet is not via telecommunication satellites, sending information up to a satellite and it rebroadcasting it back down. A lot of people get this idea that the satellites are something bouncing the signals off. They're not. They pick up the signals, process it, and then boost it and rebroadcast it down. Most of our information is actually carried in optical fibers, which is light. Actually, it's often infrared, but it can be a combination of visible light and infrared that's just traveling through these cables. A lot of them near to where we live in Portugal.
We had a big installation of a cable last year. I think it's just made it. So in a way, we are in a soup of electromagnetic information or whatever. We're in this spectrum and it holds a lot of information and it can connect things through information through these channels.
Yeah.
It's hard for us to see the soup that we're already in or to see the medium in which we're existing, but we're in this medium.
We're awash with microwaves, radio waves, gamma rays, X-rays, everything we're experiencing all the time. We're sitting in a whole mishmash of it, bouncing around everywhere.
And we've been talking about it as waves, but it's also particles.
Yeah, so if you go back to the time of Newton, there was this big debate about what was these things, light and such, and it was, well, what is it? And there were two main ideas. Could it be some sort of wave? And they knew about waves because they could see water waves, and they actually knew how waves worked very well. They also had this idea that it maybe could be made up of little particles. And you know, light can reflect or something. That's how mirrors work. And you could also imagine getting a tennis ball and throwing it at a wall. Don't think about throwing it straight on, but maybe throwing it at an angle. And you could always imagine the ball hitting it and bouncing off at another angle. So you go, well, maybe it's particles. Newton thought it was particles. And because he was so powerful in the scientific community, then that became the accepted idea. Until you get to the early part of the 20th century, where scientists were able to produce very intense, bright sources of light, which were only one color, because that was the other problem. Trying to observe light is difficult, because white light we see is actually a mixture of all the 7 colors, and the 7 colors are different, that they have different wavelengths. And so you could produce these electrical lamps that produce just one color of light. And using these electrical lamps, they actually were able to prove that light was a wave. If light was a wave, it does things called diffraction and interference, and it produces specific sorts of patterns. And the patterns that they produce prove that light was a wave. It proved it right. The real problem was that it was only a few years later that someone came along and did an experiment that proved that light was a particle, which we call a photon. And the really freaky bit is that both experiments are correct.
Yes.
So
Yes.
This is where you end up in the wave-particle duality and quantum mechanics, and your head really starts twisting. So it's not that light is a wave and a particle. That will be incorrect. It's a wave or a particle or neither.
Okay.
And if you don't observe it, then it's neither. It exists in this weird probability state between the two. Depending upon your active observation and what's useful, then understanding it in terms of its particle properties or its wave properties, and both are applicable. It just depends upon how we are observing them.
So we've been talking a lot about light, and I wanted to also ask you about the James Webb Space Telescope, which went into orbit, I think, since we spoke. I don't think we've spoken about it.
It's a while, isn't it? Yeah.
It's mostly using infrared to observe. Tell us a little bit
about it. Only
about
uses infrared, yeah.
Okay, and what's the advantage of doing that? Why is it doing that?
Most of the really big telescopes and newest telescopes that are being built are either purely infrared or partial. There's a number of reasons. Infrared, for example, can pass through cosmic dust such that we could actually see through things, that visible light would get blocked. The police could actually use infrared cameras to see cars. They're doing chases in helicopters. If someone's stolen the car, you can actually pick the infrared rays coming off the vehicle and passing through clouds or dust. That's one reason we use it. You can also see, I don't want to get too technical here, but you can start talking about these things called line spectra. So when you look at visible light, for example, we'll just see rainbows and you see the red, orange, yellow, green, blue, indigo, violet. These 7 colors are actually different wavelengths. But if you look very closely, you'll see there are actually gaps in the wavelength. There are bits where the light seems to be missing. Now, the exact positions of these gaps can actually tell us something about the nature of the objects which were producing them. So the sun has a very specific set of gaps, for example, sunlight. The gaps in the sunlight refer to hydrogen and helium and such that we see. So visible light has a very specific set of gaps, but different elements produce other gaps that actually go into the infrared, and so that could be very useful as well. Using infrared as well can be rather useful to actually observe exoplanets. And so one of the big things that James Webb is doing is actually observing exoplanets or planets which orbit stars other than our own. And we know there are thousands of exoplanets now which have been discovered. And using infrared, we can actually detect and we can look at the spheres of these planets around other stars. But in some ways, the absolute killer application of this is because of something called the cosmological Doppler effect. Now, I'll try to get to this. Scientists haven't always thought the universe was created. before the birth of the 20th century, steady state theory was pretty much the best theory in town. And the steady state theory basically said the universe has always been. It didn't have a start, didn't have an end. That was the best theory. But Hubble in the early 20th century, I say Hubble, he was the guy at the top. It was always research students who took all the data, and a lot of them women as well, by the way. He was the one who really put it all together. And using Hubble's data, he was able to notice that galaxies appeared to be flying away from the Earth. And he realized that the galaxies themselves weren't actually moving very much, it's that space was expanding and carrying the galaxies with them. So the universe is expanding. And if the universe is expanding, then in the past it should have been smaller. And if you wind time far enough back, the universe has zero size. And that's the moment of the creation of the universe. By the way, the term Big Bang was actually come up by people who thought it was ridiculous and it was supposed to make it sound stupid. So you're telling me the universe was created like a Big Bang, and now it's just become the set word. But it was actually, the Big Bang was supposed to be a joke. It was supposed to belittle it, and we've just taken the word on. Now, the thing is, okay, the early universe was incredibly hot, incredibly dense, and all there was energy. There was no matter at all. Incredibly high energy photons. Remember we talked earlier about these high energy, means stupidly short wavelengths. Now, as the universe expanded and cooled, this energy actually started to turn into particles, and this is where we get protons, neutrons, and electrons, and the universe carried on expanding. They didn't all turn into particles. Some of it stayed as waves. So some of this, I'm going to say light, but I really mean electromagnetic radiation, incredibly high energy gamma rays with short wavelengths. And these waves are zooming around. But the really weird bit to get your head around is that as the universe expanded, the actual wavelength of the waves got stretched with it. And so as the universe expanded, all these gamma rays, after a short period of time, actually turned into X-rays, which is the longer wavelength. Then a few seconds later, they turned into ultraviolet. And then the really freaky bit, a few seconds after that, it would have been visible light, and the entire universe would just would have gone bing, like the both inside a light bulb.
For us, with our receptors, they would have gone bing.
Well, yeah. Now, that only lasted maybe a minute at most, and then the universe kept expanding, and then it turned into infrared. Now, the rate of expansion we originally thought decreased, and so the gap, going from gamma rays to X-rays and all this happened quite quickly, but the other steps took significantly longer. So eventually they turned into infrared, and then eventually after that into microwaves. Now, the thing is, after 13.6 billion years, which is what, looking at the rate of expansion of the universe, we estimate the age to be, the theories predict that these incredibly high energy short wavelength gamma rays, after 13.6 billion years, should be microwaves. So astronomers went, the universe should not just be full of microwaves, but no one had seen them. So back in the 1960s, a couple of engineers who were trying to build microwave transmitters and receivers, because they knew that these were really used for satellites, which they still are, they built a very sensitive microwave detector. It's like a satellite dish, sort of thing. Very odd looking thing. They pointed at the sky. The really annoying thing was is that they kept getting this background microwave radiation. It was a real pain because it was messing with all the results. And they tried to get rid of it. They even cooled down their apparatus, and they thought it might have been pigeon poo on the sides of it. They couldn't get rid of it. But the really weird thing was they noticed that wherever they pointed it in the sky, they kept getting these microwaves. And so they published this, and it was like, this is weird, isn't it? And of course, all these cosmologists went, we predicted this decades ago, and this is the cosmic microwave background, which now is a massive part of research is looking at the cosmic microwave background. Back to James Webb. So we got the Hubble telescope, for example, named after Edwin Hubble. The Hubble telescope has seen objects at 13 billion light years away. So basically, we're seeing distant galaxies, not individual stars now, by the way. We're talking distant galaxies made up of hundreds of millions of stars. We can actually detect the light coming from them. So basically, we're seeing back close to the beginning of the universe. But there's a limit of how far you can actually do that with visible light. The very first stars that formed after the universe cooled down enough to start forming stars, and gravity basically was able to win and collapse the hydrogen together to form stars. These stars formed so far back in time that the light which set off from these stars, by the time they get to us now, the light would have actually been stretched out of the visible and into the infrared. And James Webb observes in the infrared. And so what James Webb will be able to do is, and the great hope is that it will be able to view the first stars and galaxies that formed after the Big Bang. And that will give us some better idea of how the universe evolved and how the space which we live in will be. Now, we're not there yet. The distance records, basically, for the furthest objects ever seen, keep getting broken by James Webb every few months. And we keep pushing it back further and further and further. It's 13.3, 13.4 billion light years, I think, are the furthest objects we've seen. And we're going to keep pushing it back further and further. So they are looking at very distant objects. It's causing a bit of a problem. There's a real problem at the moment in cosmology. There's a real difficulty. Results taken 20 years ago, longer, getting on 25 years ago. A set of scientists actually were studying distant supernova explosions in distant galaxies. And by looking at the light coming from these and also noting the Doppler shift of the light coming to, cut a long story short, by looking at the data, they realized that the universe didn't seem to be slowing down in its rate of expansion. Now, I was taught that the rate of expansion of the universe is slowing. That's what I was taught. I taught that for the first 10 years or so of my teaching. And then scientists came along where actually the rate of expansion is speeding up. I remember going into school and saying, don't worry, wrong, don't worry. It's wrong. It'll prove to be an error and they'll have to redo it. No. Turned out it wasn't an error and everybody kept repeating it. The rate of expansion is speeding up. Now, the rate of expansion of the universe is increasing. It's meant that we don't really know why. So we had to invent this concept called dark energy to try to explain this. And we don't know what dark energy is. We don't know what it is, but we've invented it to try to fix gaps, if you like. The real problem is that the latest data from James Webb is giving us one set of data points suggesting the rate of expansion of the universe, which gives us this value for this thing called the Hubble value or the Hubble constant, which tells us about the rate of expansion of the universe. And the James Webb data has given us new values of this. Remember I talked about the cosmic microwave background? There are ways of using the cosmic microwave background and the variation to give another value for the Hubble constant. These two numbers are the same. They should be, but they're not. And the latest cosmic microwave background data and the latest data for James Webb and other telescopes, these numbers are going like this. They're getting further and further apart. And this is a real big problem to the extent that people are suggesting some really freaky stuff. There are people suggesting we need to rewrite Einstein and Newton and that we need new laws of gravity. There are people saying that we don't understand supernovas. So it's quite an exciting time. But the thing is, what's brilliant is that the scientists don't freak out about this or worry about it. This is brilliant. This is what we live for. It's like, we don't know. I know we've said before, and I'm sorry I'm repeating myself, but greatest answer in science is, I don't know.
Yeah.
The scientists, this is not a problem. It really is an exciting time. Things could change a lot, but James Webb and lots of other instruments at the European Southern Observatory are building the largest ground-based telescope that you've ever seen. It's called the Extremely Large Telescope. It's the one that's going to supersede the one before it, which was called the Very Large Telescope. Astronomers are not very inventive, I'm afraid. This thing is massive. It's good at observing the visible and the infrared. It's on top of a mountain in Chile, in the region of the Atacama Desert, where all the Nazca lines are. This thing is like a primary mirror, which is, I'm not sure of the number, I'm really sorry. It's about 50 or 60 meters across. Primary mirror.
Yeah.
It's incredible.
Do you feel that in your lifetime you could see some quite new theories or...
I've seen them already, and I think there's more to come. The seismic shift, dark matter already existed as a concept. Zwicky back in the 20s or whatever was talking about dark matter. I must apologize. I might get some dates and things wrong in this. Dark matter is it would plug the gap. Stars weren't orbiting galaxies quite right. And so it were like, we either reinvent gravity or we say there's some stuff we can't see. So we invented dark matter. We still don't know what that is. It's so amazing. We still don't know what it is. Modern cosmological theory, the standard model of cosmology, still assumes that dark matter exists. Then dark energy was produced. We still don't know what it is. But all the modern theories, cosmology and astronomy, basically assume it's out there. The problem is we can't build a telescope to see it because we don't know what it is. We can't observe it. So the electromagnetic spectrum that we use to observe things around us, dark matter doesn't seem to be producing it. So you have to observe it in different ways. So the way which we think about observation has to change, because when I say observe, I'm guessing most people out there listening to it are thinking I'm looking at it. It doesn't necessarily mean that. Observation can mean a number of different things. And so observing it can mean actually observing it gravitationally. Now, we say that dark matter exists because there's gravity coming from something causing objects to move in ways we can observe, but there's gravity coming from something which we can't see. So that's why it's called dark matter, because it is not producing any electromagnetic radiation, but we can detect the gravity of it. Now, the question then becomes is, what is dark matter? Or perhaps we just don't understand the gravity. That is another possibility. But I'm afraid the people who are saying that, these are the outcasts. These are the sort of like scientists chasing with flaming torches and pitchforks. And it's like, can't say that Einstein and Newton are wrong, but some people are saying that. I think that Einstein and Newton probably is correct, but I've said that before to my own students and turned out to be wrong. So I think they probably are right. I think it's just that we don't know what it is. And then we then may need means to detect it or observe it. Have you heard of gravitational waves? If you get a skipping rope or something, you can flick the rope up and down and you can actually see almost like the rope, almost acting like water waves, can't you? Flicking through along the rope. Can you imagine what I'm saying there? You can flick a rope up and down. Does that make sense? You can create waves in this physical medium. Now, the weird thing is that you could think of space and time as being almost like a physical thing. It's not really, but you can view it in a way that it is almost like a physical thing. Now, it does mean that when you get some of these really energetic events that like neutron stars colliding or black holes falling into each other, they can produce so much sort of explosive energy that it's not just electromagnetic waves that travel through space. The fabric of space itself basically starts to shake. And so the waves can pass through space itself. This is not light or anything. It's space itself moving, and it can pass through into these waves. And so in a weird sort of way, in the same way that if you're floated in the water and waves come past, you will move a little bit. If a gravitational wave passes through the Earth, in theory, we can detect a slight actual physical shift in position. And so they build gravitational wave detectors, and you basically get like a laser in the detector and the opposite ends of a very long tunnel. And so if you shine, we know how fast light travels. So you shine the ray of light down the tunnel, we know exactly when it should get there to the detector. But if a gravitational wave passes through the detector, the physical distance between the laser and the detector might get shorter or longer. So the time at which the light gets there changes. And they've actually detected this. So we are now, this is a separate way to perceive information that's coming from space. And we've done it, and it's been done. And there's a space system going to be going up really soon, where it's going to be satellites orbiting the Earth, which are going to be the detectors and the receivers. It's going to be even more precise.
Wow. And there could be this electromagnetic soup that we're in that I was talking about, this kind of medium that we're in. We're also in some kind of gravitational soup.
Yeah.
But you don't think that there's any way that the electromagnetic soup and the gravitational soup are on a continuum. You think that these are, one relates to matter and one relates to energy.
But they are interconnected, and they will affect each other. Because in the same way that gravitational waves can distort space in such a way that how the electromagnetic waves are traveling through it changes. And so there is going to be some interaction between the two. But gravitational wave telescopes is a whole thing. They're going to be these massive space-based systems that are going to tell us about very energetic events and potentially might tell us something more about the beginning of the universe. Sorry, I'm doing air quotes here. If the universe did have a beginning, there are some people going, maybe that's not the best way to think about it.
Yeah,
so steady state is actually back a little bit.
Wonderful, wonderful. And that's what science is so inspiring, is when everything's up for grabs and we get new data and it's a chance to examine our models. Sometimes they get confirmed and sometimes we get new information that we didn't expect.
We have to, sometimes we literally have to throw away and start again.
Yeah.
Generally, it's more nuance. Newton is still great for most situations, so we're not going to say Newton's wrong. We still talk about the Copernican view of the solar system. Okay, he didn't get it exactly right, but fundamentally, yeah, he did. And granted, we needed Kepler to give us a better idea, but it's all building, and it's not like one person is wrong. I think this sense of like people being wrong and right. Yeah, there are facts. Yes, I can give you facts, but they are bounded by a certain set of scientific principles, and science's views can change. That doesn't mean that any idea is acceptable. The scientist isn't going to say that gravity is created by pink unicorns. But the scientific community would say, "Please show us your data, please." Yeah. This is where I very much put my hand on my heart and say, my view system is I'm very much an empiricist. I'm like, show me the data. Give me the data, I'll go with it. I'm fine. Show me the data.
Yeah. That's where we're at, that we're getting these instruments that are giving us data from further back in time, or when you're talking about gravitational telescopes, giving us data that we haven't had a chance to really look at before. So,
didn't even realize that was even the set of data that we could even achieve.
So it's very exciting times. And eclipses are like that as well, because they have that special moment of experiencing something that we don't expect. And you're going to go experience an eclipse total.
And this is the thing. And I could have tried to take loads of instruments with me, but in the end, I want to experience it as like a human being, person. That's mainly what I want to do. I want to just experience the wonder of it. And as a scientist, I still see awe and wonder.
It's having the experience of being awe-inspired or being awed. And nature has that for us. Eclipses have that for us. And that this feeling of connectedness to the glory of this experience. And I think people's philosophies do get impacted by scientific theories, like what you were saying, the mocking of the Big Bang is partly because it was very challenging theologically and to people's place in the world and their place in their understanding of life. And so as we get more information about all of these new things that we're looking at the moment, it'll be really interesting to see what humans make of the meaning of that. I'm very interested in that. As all of this information comes along, how do we make meaning from that?
I do wonder that within my lifetime, will we find data that pretty much proves that there is life elsewhere? And it certainly could happen in my lifetime, I think.
Yep.
It's probably going to be close to home. It will probably be Mars, I think, because there's some very tantalizing sets of data that's come out in the last few years that it's hard to explain without saying it's life.
I love that, Stephen, and this is where I think I'm going to press the pause button and invite you back, because Stephen doesn't know I still have a whole heap of questions for today. And partly based on Voyager as well, because Voyager's crossing boundaries that
I know. All right, but just drop you with a little thing, because it links back to everything you were saying about the waves and the light and everything.
Yeah.
In a couple of months' time, Voyager will be one light day away.
Yeah.
One light day. So this wonderful beam of light or radio wave, it would take one day to get to us. So to me, I know it doesn't really matter. It's just another point. But to me, it does matter. One light day away. That's how far we have projected our humanity, our technology, if you like. And most carrying those gold discs with music and speech and an essence of what humanity is. It's set to get there in space, but one light day away. So we started talking so much about light. So a beam of light would now take one day to do that
Definitely.
journey. I think that's...
Yeah. Let's reconvene because I really do want to talk about that. I think there is some really important stuff. I want to talk about, will we find what we can define as life beyond planet Earth in our
That's a good one
lifetime?
to talk about it.
I want to talk a little bit about black holes as well. So there's plenty still to talk about. But maybe if we can leave you with something from this podcast, it is that inspiration to connect with the awe of where it is that we are and whatever that means for you. And for some people that is through space. And I know Stephen shared on the podcast before that space has been a way for you to connect to awe-inspiring connection to life.
Yeah.
And for some people, they get that through the astrology, using the metaphor of astronomy and astrology together as a way to connect to that awe. And for some people, it's that turning within, that there is a universe inside of ourselves. And when you're meditating, you can almost feel that you are a detector of frequencies as you get more and more quiet. And this, what we've been talking about today, about the wavelengths, is something that people who meditate or have a yoga practice might relate to on even physical levels, because yoga it's just all about connection, and whether you're going to get that connecting to the universe and the galaxies, or you're going to get that connecting on the inner experience of being here, I think that's very enlivening to feel awe-inspired by life.
Absolutely.
Yeah. Stephen, thank you so much for letting me quiz you about every astronomy question that came to mind.
Always.
I can't wait to have you back to talk about more of these exciting things. So thanks to Stephen, and also thanks to everyone who's listening, and look forward to seeing you again. Okay, bye everyone.
Bye-bye. Bye.